Hey everyone, we're here again today with Graham Medlin, engineer at Wiser. I'm Seth Holler, CEO of Wiser Systems, and today's conversation is to talk about longevity of ultra-wideband tags and how we engineered them. But in general, there would be some similarities to other tags out there as well. So with that said, Graham, I'll set the stage. A lot of our customers buy a lot of tags from us, thousands of tags, and they're clearly in the business of keeping these tags, being able to track things without the worry of like constantly replacing tags or replacing batteries. And so with that said, go ahead. How do we design it? How do we engineer it? What are the thoughts behind those designs?
Sure, yeah. I mean, it's super interesting that we can make this one little battery last 4 years, whereas your phone, you were charging every night. That's not going to work for a customer.
Very interesting indeed.
So there's sort of a system level design engineering. There's firmware decisions, and then there's the actual hardware is implemented. On a system level, the design of our system is what we call a time difference of arrival, TDOA, where the tag itself is only transmitting. It's not receiving, and that saves a lot of power. So you're relying on the powered antennas around the facility to do most of the heavy lifting, most of the work.
So TDOA, time distance of arrival, that can be thought of like in layman's terms a little bit like a reverse GPS system where you have multiple devices out there that are fixed, and then you have a single one pinging, as opposed to GPS where there are multiple satellite objects pinging and one receiver.
Yeah, exactly in reverse of GPS.
Okay. And so, well, let's dive deeper. You said there are multiple levels. There's like the firmware level. There's also the hardware elements of it, and then you talked a little bit about the protocol being chirping only. So that in itself is a power savings element. So choose any one of those and you dive a little deeper into that.
Sure. I mean, the hardware is fun. Both the microcontrollers controlling it and the EWB radio have very low power sleep states when they're not doing anything. So the goal in designing both the hardware and the firmware is to have it sleep most of the time, wake up, make that chirp using as little power as possible, and then go back to sleep. You think of the battery as a water tank storing water, in this case storing energy. You're taking just a tiny little sip every little time to try to make that stretch out for a long period of time. And the batteries we use, those coin cell batteries, are great for this because they have very low discharge rates. Like if you leave your phone sitting on the table for weeks, it will slowly drain. But these coin cell batteries don't. They can last for years and years, which means you really can take that little bit of sip and then leave the rest of the water there in the tank.
Okay, and then you mentioned these sleep cycles. So, I mean, from an electrical engineering perspective, this tag is always consuming power. It's either consuming power in an active state when it's on transmitting, but also it's consuming power in the sleep state. Mm-hmm. So it's not necessarily zero, but it's almost zero, right?
Almost zero is the right way because it's 10,000 times difference power consumption. I'm not sure I have that math right, but it's a dramatic difference between that power usage in the sleep state and when it's actively transmitting a radio.
But part of the design process of these tags is making sure that when you select the components and you design it, you have to make sure that sleep state current consumption, I guess they call it quiescent current, is really low, right?
Yes.
And how difficult is that to make happen?
It's not difficult, but it takes care. It's very easy to put a resistor here or a capacitor there that's the wrong kind of capacitor and just have a constant little bleed of current. And it's not a lot of current, but over years it's a lot of energy wasted. And so you're going through every single component and checking that this isn't wasting that little bit of power.
Okay. So there's that one power element. Now kind of jump to the active state. When it's on, what methods are there to reduce the total amount of power while it's on, or what do you pay attention to when designing the firmware to make sure it consumes less power?
Sure. I mean, the primary one is just the amount of time it's on. So while it's transmitting, that information that it's transmitting. So we've designed a protocol that is transmitting as little information as possible, so as fast as possible. It's who am I? what my battery state is, and that's it. And then it shuts back off immediately.
And even when it actually turns on, it doesn't waste any time, right? It doesn't turn on and say, I'm going to sit here for a few seconds. It simply turns on, and as soon as it can transmit, it transmits, right?
Correct. Little sound wastage as possible.
Got it. And then the other element is, we didn't talk about this too much, but there's sensors on board to tell whether it's in motion or it's still, right? And so how does that play an impact?
Yeah, that's a great tool. Since we are locating a tag, if the tag is not moving, we don't really need to update as often. And so there is a motion switch on this case. It's literally a ball inside of a cage that can roll back and forth to tell if the tag is moving. And if the tag is not moving, the microcontroller, waits for that signal. If it doesn't get it, it just sleeps for a much longer period of time. That's configurable, but typically like every 10 seconds you might update if the tag is not moving because it hasn't moved. And maybe every 1 second or faster you update if the tag is moving around the facility.
Okay, got it. So the logic here is you do not need to ping or update the location as much if it's not moving because it's pretty much in the same location.
It's in the same spot, yeah.
And then that way you're not consuming as much power during the active state, or the active state's not on as much, so you're consuming less power or saving more energy.
Yeah,
so
exactly.
It lasts longer.
Yeah.
Is that right?
Yep.
Okay, and so that's kind of the algorithms and the hardware. And then you did touch upon TDOA as well, where it's simply just transmitting and doing nothing else. And that's a big power saver
yes.
as well, right?
And that does require the system level design, right? Is that for that to work, it has to be supported by all of these antennas around the facility that are themselves communicating and comparing notes on those tags for that to locate the tag accurately.
Right. So we shift the power burden from the tags, and so they can stay very low power, to the surrounding infrastructure that actually receives the tag information and does something with it.
Exactly.
Well, I think we're out of time today. I really appreciate it, Graham, that explanation, and we'll be around next time. So thank you all so much. Thank you, Graham.
Thank you, Seth.